Hi all, welcome to my YouTube channel Know About Embedded System. In today's video, we're going to discuss again about ARM architecture, nothing but ARM Cortex-M3 architectural overview, but today we'll be discussing about registers. So without further delay, before starting the video, if you're a new viewer, so kindly subscribe to my channel to know more about embedded system. Let us start the video here. So this, you know that already, this is your ARM Cortex-M3 processor, and inside this core, especially this part, so this part in the ARM core, we will find number of registers. In the previous video, we have already discussed about general purpose registers, which are from R0 to R16. In today's video, we are going to discuss some special registers about this. So there is a register called PSR, pre-mask, fault mask, base pre, and control register. So we'll try to understand all these things, and just keep it in mind, the registers will be available inside the ARM core. So these things are not visible in the architecture, but these registers are available in the ARM core. So let us continue now. Okay, the first register called as pre-mask. So in the list, whatever you are seeing, the first one, so this is called pre-mask. So pre-mask, what do you mean by pre-mask? Pre-mask stands for priority mask. You can see here the pre-mask stands for priority mask, and it is 1-bit register. This is only 1-bit register, and this will tell you, or this is going to control non-maskable interrupts and hard fault interrupts. So what do you mean by non-maskable interrupt and hard fault interrupts? That I'll explain later in the interrupt part. Just keep it in mind, these are all the high priority interrupts. Non-maskable interrupts and hard fault exceptions are very high priority interrupt. And whenever this priority mask bit, so that means this bit or this register, what you are seeing, so this is a single bit register. Whenever this bit is 1, or when this bit is set, this is going to enable only non-maskable interrupt and hard fault interrupts, and other interrupts will be in disable state. You can understand here other interrupts. So this basically your LPC or your ARM Cortex will support up to 255 interrupts. It will support totally 255 interrupts. Out of this 255 interrupts, whenever you are enabling pre-mask bit, it will enable only non-maskable interrupt and hard fault interrupts. So other whatever you will be having around 253 interrupts will be in disabled state. So that is, for this purpose, we are going to use pre-mask register. The second important special register which is available in ARM Cortex is fault mask. So we have understood pre-mask, and now we will understand what is a fault mask. So what do you mean by fault mask? Fault mask means it is also similar to pre-mask, but there is a slight difference here. So pre-mask will enable 2 interrupts. One is non-maskable interrupt and one is hard fault interrupts. But fault mask will enable only 1 interrupt, that is called NMI. Fault mask register, or it's again 1-bit register. This fault mask register will enable only non-maskable interrupts. So now third one is base priority, or we will call in a short form, it's called base pre. Here you can see what do you mean by base pre. So base pre means, so this part, base pre means priority register. For example, so I just try to understand the definition. Base pre stands for base priority register, and basically this is going to be an 8-bit register. You can assign totally 255 different priorities. 255 priorities you can assign, and what it indicates, for example, to this base priority register, I will assign something called as 10. So if you assign the value 10 to the base priority register, this is going to allow from this 10 whatever numbers are coming, like 9, 8 and up to 1. So this base priority register will allow all the lower interrupt numbers, nothing but interrupt number 9, interrupt number 8 and up to interrupt number 1. Interrupt priority levels 9, 8 and 1. And it will not allow, your base priority will not allow a higher priority, in the sense lower priority with higher number. Okay, in our embedded system, lower the number, higher the priority. The blue color what I'm highlighting, these are all higher priority values. Lower the number, higher the priority. Okay, so in this way you have to remember, in our embedded system always lower number will have highest priority and higher number will have lowest priority. So example, if I consider here, if I consider 10 as a number, or if I assign 10 value to base priority register, your microprocessor or your ARM Cortex processor will allow 10, not from 10, below 10, that means 9, 8 up to 1 interrupts priorities are allowed, and above and then equal, that means 10, 11, 12, 13, your Cortex will not allow for the interrupts, or it is going to disable the interrupt. So this is called as base priority. So we are going to assign some base level to the priorities. Below that it is allowed, above that number it is not allowed. So that's what he is telling. It defines the masking priority level. The base priority will define the masking priority level, and when this is set, it will disable all interrupts of the same or lower level. That means larger priority value. So it is going to enable higher priorities, okay, and it will disable lower priorities. So that means lower the number, higher priority, and higher the number, lower. So that concept you have to remember here. If this bit is 0, the complete priority will be disabled. So this is called as base priority in ARM Cortex. This is the third special register. The next one, let us see the control register. This control register is a 2-bit register, and this will define two important things. The first important thing, already I have told you, in our ARM Cortex we have two different modes. One is called three different modes are there, but broadly it is classified into two. One is a thread mode and one is a handler mode. So under thread mode we have two options are there. So two small modes are there, that is called privileged thread mode and user thread mode. So this user thread mode and privileged thread mode will be defined by control register bit number 0. So control register, basically it is a 2-bit register, and in these 2 bits, the bit number 0 will define privileged thread mode or it is user thread mode. If the control bit 0 is 1, it is called user thread mode, and control bit 0 is having the value 0 is called as privileged thread mode. Similar to this, so we have bit number 1 here. In the bit number 1, we're going to define two stack pointers. Already we have discussed in the previous general purpose register, we have two stack pointers. One is called main stack pointer and one is called process stack pointer. This control bit number 1, control bit 1 is going to define this same thing, MSB or PSB. If the bit is 0, if control bit 1 is 0, then it is going to be default or a main stack pointer, or if the control bit 1 is 1, then it is called as PSB. Like this, we have 4 special registers and one status register is there. So status register I'll be explaining in the next slide. So pre-mask, fault mask, base pre, and control register. Okay, these are all the special register in our ARM Cortex. Then the next one is the program status register. So this program status register, it is subdivided into 3. You can see here. You know that already program status register is nothing but status information of your processor. So this status register is divided into 3 parts. One is application status register, one is interrupt status register, and one is execution program status register. Okay, so what do you mean by this application program status register? So you can see here, application status register will give you only the flags N, Z, C, V, and Q. N stands for negative, Z stands for 0, C stands for carry, V stands for overflow, and Q stands for SysTick timer. Negative, 0, carry, overflow, and SysTick timer. So only this 5-bit information will be provided by the APSR. Okay, and similar to that, we have interrupt program status register. It is called as IPSR. This IPSR will give exceptional information. So exception information it will give. So these exceptions includes regular hard fault, non-maskable interrupt, or the interrupts which are generated from the peripherals. So that information will be provided by IPSR. And finally, the third one is called execution program status register. EPSR we will call. This EPSR will give information about thumb mode, whether you are running in a thumb mode or in ARM mode. So that information will be provided by EPSR. And along with that, there is something called as IT and ICI. So IT stands for if then instruction. Whenever you are using if and then instruction in assembly language, this bit is going to set. And similar to that, ICI, interruptibility and continuability instruction. So whenever you're using IT and ICI instructions, these flags are going to set, or these bits are going to set. So like this, program status register is subdivided into three: APSR, IPSR, and EPSR, but all put together, when you see a complete 32-bit in a single register, that is called as XPSR. XPSR, or you can say program status register. In this, all bits are combined. Here you can see this is the APSR, and this is your EPSR, and this is your IPSR. So all three registers combined, and it is called as XPSR. Stands for program status register. So this much. These are all the different special registers available in the ARM Cortex processor. Now I'll take you to the software. In the software, I'll show you how these registers looks like in the software. So in the software part, I have already explained a video. There is a video. I'll update the link in the description box. You can watch that video, how to create a project and how to set up the software part. That information I have provided in the video. So now currently, so how it looks like, what are the different registers, that part we will see. Now you can see this is my core. Core is nothing but core Cortex processor. Inside this, you know that already we have we have different registers. So here you can see these are all the registers: R0, R1, R2, and so on like that, and up to R12. Okay, then here you can see we have R13. We have R14. R13 is a stack pointer, R14 is a link register, R15 is a program counter, and then followed by XPSR. Okay, then if you expand this XPSR, here you can see the currently whatever we have seen: negative, 0, carry, this is called overflow, SysTick timer, thumb mode, IT, and ISR. All these informations are available in this XPSR register, and then stack pointer, link register, program counter. These are all your general purpose registers, and stack pointer and link register. Then, so here you can see I have already told in the previous explanation. Just now also I have explained we have two stack pointers. One is a main stack pointer and one is process stack pointer. These two things you can see here. And then our interrupts related registers, base pre stands for priority register. You can see it is a 8-bit in nature. We can assign any value here, and based on that it is going to disable some of the above that number is going to disable, and below that number it is going to enable. Then pre-mask, priority mask, then fault mask, then we have control register, right? And then finally, what are the different modes? Just different modes. Here you can see the mode parameter will define which mode the processor is running. Currently it is running in a thread mode. Privilege, you can see it is running in a privileged thread mode. It is running in a privileged mode and it is running in a thread mode, indicating that privileged thread mode. And stack, by default it is going to use main stack pointer. Okay, so like this, different registers are classified in the ARM Cortex processor, and this is a view in our software. Okay, so I think this video is interesting to all, so please like this and subscribe to my YouTube channel and gain the knowledge on embedded system. So let us meet in the next video. Thank you for watching.